Yeah.
Hello everyone. Today we have with us Kayo. Kayo is a master's student at Carnegie Mellon University, where she is currently working on context-aware multilingual dialogue translation. Before that, she obtained her Bachelor of Science in Math and Computer Science from Ecole, that's in Paris. And her long-term research goal includes to break down the communication barriers between people and between computers and people. She's generally interested in topics in multilingual NLP, low resource languages, and AI for social good. Today, we are going to discuss some parts of her bachelor's thesis, which was centered around sign language translation using transformers. We're glad to host you, Kayo. Kayo, please proceed.
Yeah, thank you very much for having me, and thank you to everyone joining me today. I'm very happy to talk about my research. Okay, so I was going to briefly present myself at the start as well, but Shambari did a very good job. Um, so you can reach out to me anytime you want after this talk on Twitter if you want. I'd be more than happy to talk about my research or any of my other experiences, so feel free to do that. Okay, so today I'll be talking about the research I did at Ecole Polytechnique for my bachelor's thesis. And I am proud to announce that this thesis was selected as this year's winner in the computer science category at the Global Undergraduate Awards. So
Congratulations.
thank you. So my full thesis paper is not yet available publicly, but it will soon be published in the undergraduate library, so please keep an eye out.
Yes.
Right.
So I'll begin by introducing the motivation behind my work. So communication holds a central position in our daily lives and social interactions, and it is the essence of human interaction. And yet, deaf communities are often isolated from a predominantly hearing society because of language barrier. And although deaf communities have developed their own language, sign language, as a means of communication, the use of this language often remains restricted to these communities. And existing accommodations are only imperfect solutions. So lip reading is prone to errors, and closed captioning or text-based communication, they all rely on the deaf's fluency in spoken language. Oh, so throughout the talk, I'm going to refer to our oral language as spoken language, but it doesn't, it can refer to the spoken version or the written version.
Got it.
And
Got
just
it.
contrast it with sign language.
Got it.
And sign language interpreters, they're often unaffordable or they compromise individual privacy. And deaf children are sometimes even encouraged to learn to speak and read lips so that they can be better integrated in society. But this only amplifies what we call language deprivation syndrome, where a deaf person who did not have full access to a natural language during their critical period of language acquisition, which is usually the first 5 years of their life, they have difficulties in their later life. And so, today the deaf community face daily issues and miscommunication. So sign language processing is an important research area that can help give more social currency to sign language and also preserve this rich language. And recent advances in machine translation for spoken language, they've shown to significantly improve comprehension across different spoken languages. Like I use Google Translate all the time. So my work is motivated by the success of machine translation, coupled with the need for sign language translation tools to provide assistive technology that can help deaf people to communicate in their own language. So now I will provide some background about sign language research. And the research about sign language is very much in its infancy today in general, so not even for machine learning specifically. Because in 1880, the Milan Conference, they banned sign language to be taught in deaf schools to teach speech therapy instead. And it was not until Stokey's work on American Sign Language in 1960 that sign language started regaining social recognition and research interest. So that's very recent. And even today, only 41 countries officially recognize sign language as an official language. And moreover, contrary to many assumptions, there is not one universal sign language. But in fact, so Ethnologue lists 144 different sign languages, and where most of them are not mutually intelligible. So here's a, wait, oops. Let me see. Yeah. So here's a video of I love you being signed in 60 different languages. So
Very cool.
solving the challenge for one sign language, it doesn't mean that we have solved the challenge for all sign languages, just like in spoken language. And for this reason, research in sign language translation, it would not only improve communication between the deaf and the hearing, but also between different deaf communities around the globe. Okay. So other challenges. So unlike spoken language, sign language is a multi-dimensional form of communication, which relies on both the manual and non-manual cues, which presents additional challenges in computer vision. And sign language relies not only on hand movements, but also other means of body language, such as facial expressions, body posture, head and upper body movements, word mouthings. Yeah, and despite the common misconceptions, sign language is often not related to its spoken counterpart. So like English is not derived, no, sorry, American Sign Language is not derived from English. And it often developed independently with its own grammar and linguistic rules, which is why it also poses an interesting challenge linguistically. So for example, the syntax of American Sign Language shares more with spoken Japanese than English.
Oh,
Yeah, and it also has like lots of like interesting like grammar like phenomenons. Like one
yeah.
example that I like to give is co-reference. So for example, like in spoken language, we would say like, oh, so Alice and Bob. Alice is French, Bob is American, she is tall, he is short. Like we don't repeat the pronoun. And what they can do in American Sign Language, for example, they can say, so like, I don't know if you can see my camera well, do a
Yes,
demo,
yes.
but they
I can
say
see it.
like, oh,
Yeah.
so there's two people. And like first here we have, we can finger so like Alice and Alice. And then here we have Bob. And then like instead of finger spelling the name each time, we can say, so the person here is French, or the person here is American, and the person here is tall, or here is short.
Okay,
So like
okay.
you can see how that will pose a problem in
Yeah, yeah, yeah,
sign
yeah.
language processing, because like the model has to keep track of, oh, so this is Alice and this is Bob.
Got it, got it, got it.
Yeah.
So, do you also have you also tried to see when there are two people in a frame and they do different signs?
Mm-hmm.
So, is that a problem as well, or?
Yeah, so that could be a problem, especially like if you want to identify like kind of the boundaries between different sign people. So like,
Mhm.
yeah, so I guess like in the computer vision system, they must know like who are the individual signers, and
Mhm.
also like so I think like in the CV talk, like one of the previous talks had Amit who presented
Yeah.
Mhm.
yeah,
For
like sign language
detecting who
detection.
is signing. Yeah.
Mhm.
Yeah, so that's also like another challenge of knowing like when people are signing and when people are just moving in general.
Mhm.
Yeah.
Got it. Thank you.
And yeah, so like because of the novelty of the research in sign language, and also the lack of standard and the resources it takes for sign language annotation, because we don't have many sign language experts in the world, available data sets are limited in size, vocabulary, and complexity, which is another challenge.
Mhm. Yes.
And so like one specific challenge about the sign language translation task is that the problem of representation in machine learning, because sign language has no written form. So how can we like give the information about sign language to a model that needs written form? And transcribing the full meaning of sign language into text is not straightforward because of, like I said, its multimodality and nonlinearity. Well, text is like linear. So to address this issue, one like method that is used is glossing, where we transcribe the meaning of each sign by using spoken language, which you can see an example here. So like each sign is associated to one gloss. But glosses still differ from translation, as you can see like the difference between the gloss and English equivalent, because they only indicate what each part in a sign language sentence mean, but it does not form an appropriate sentence in the spoken language. And so like we use glosses for our machine translation framework, because we can easily control the level of linguistic detail in the annotations. And they also form a linear sequence, which is kind of similar to spoken language. But one problem that I'm going to talk about today is that there is inevitable information loss when we represent multi-channel sign language by a single dimensional stream of glosses. And this is going to become very obvious in the work I'll present. Okay, so I'll move on to sign language recognition. So this is used to automatically obtain the sign language glosses from videos. And the first approaches in SLR rely on handcrafted features, and they use hidden Markov models to model the dependencies or dynamic time warping. And more recently, deep models like convolutional neural networks have shown to be very effective, so that we don't have to rely on handcrafted features, and they can model the spatial temporal representations from the sign language videos. And for continuous sign language recognition, this is where we identify a sequence of signs rather than like just isolated single signs. So that it has an additional problem of like knowing where signs end and when there's the next one. And most existing works first learns to align frames to signs and then perform a single sign recognition. And then they combine the outputs to construct a sequence of glosses, where there are also others that perform the task in an end-to-end fashion using deep learning architectures. But most works in SLR and continuous SLR, they mainly focus on the visual recognition task. So they don't take into account the underlying grammatical and linguistic features of sign language. So this is where sign language translation comes in. So since the obtained glosses still differ from spoken language, so sign language translation has an additional step here, where you can employ neural machine translation on the glosses. And this task was only introduced in 2018, where they used a recurrent neural network based model to perform the translation part. And subsequent works got improvements in sign language translation by only enhancing the sign language recognition system. But when I did this work, like no further study on the translation system has been performed yet. And while sign language recognition is monotonous, so like each frame corresponds to each sign in like that, the word order usually changes during translation, and the word forms also depend on the context. So machine translation presents a significant complexity, as the system has to like compute the probability of different word orders and grammatical forms conditionally to the relationship between the words in the sequences. And at the time I performed my research, there has been no successful application of transformers to sign language before. So I was really inspired by its success in spoken language neural machine translation to center my studying on using this architecture for sign language translation. Yes, just to give a brief background about neural machine translation. So these are models that use neural networks to perform automated text translation. And they typically use a encoder and a decoder architecture, which are also used known as sequence-to-sequence models. So here we have a sequence-to-sequence model that has attention, where the encoder reads the input sentence one word at a time to produce a hidden representation. Then the decoder produces words in the target sentence until the end of sentence token appears. And at each step, the decoder uses the previous predicted words and also the context with attention that the encoder has computed in order to find the next best word. And the early approaches use recurrent networks from the encoder and the decoder, and also convolutional networks. But the problem with these networks is that they're unable to model long-term dependencies in large input sentences without causing an information bottleneck. So to address this issue, more recent works use attention mechanisms, and where the attention function calculates the context-dependent alignment scores between the encoder and the decoder hidden states. So in other words, the attention mechanism assigns scores to different hidden states, and they amplify like states that are more relevant to the word being translated, while like reducing other like words that are not very relevant. And so the transformer is a model that was introduced that only relies on self-attention and does not implicate any recurrent networks. So that's where the name of the paper comes from. Attention is all you need. And it's obtained state-of-the-art results in machine translation. So first, in the first part of this talk, I'm going to talk about gloss-to-text translation, which is mainly on my work that has been presented at the Sign Language Recognition, Translation, and Production workshop this year at ECCV. I'm not sure like how many of you are familiar with the transformer architecture, since like it's
Kayo, please give a brief background, because I am also not that well versed with transformers.
Okay, yeah, so I can like provide a brief like explanation of the architecture.
That would be great. Thank you.
Yeah. Yeah, so like I said, it's a sequence-to-sequence model, you can see here, that differs from previous models because of its use of self-attention layers instead of any recurrence. And yeah, so I'll briefly explain, but like I really suggest you to read the original transformer paper. Yeah. So it's composed of an encoding component and a decoding component. And both the encoder and the decoder stacks are composed of, let's say, n identical layers. So in this diagram, n equals 2. And each word in the input sentence is first embedded into a vector before being passed to the first layer of the encoder stack. And the output of the last encoder layer is then used by the decoder layer during its attention operations. So this is like seen through the arrows here. And that's like how the decoder gets the generations.
So this is different because there is no memory involved. Is that the key difference?
Oh yeah, so the thing is, so like transformer has no like recurrent gates. So like the advantage is that like it can process longer sentences.
Got it. Thank you.
And like that's mainly done through the self-attention mechanism, which I'm going to explain now. So like first, let me give you like a quick intuition behind self-attention. So attention in general is a mechanism where our model processes data by selectively focusing on different subsets of the input. And it was introduced in the NLP community to help memorize long source sentences, but it's also widely adopted in the computer vision community to focus on the relevant parts of a given image, for example. And so this example I took, self-attention can help the machine translation model resolve the ambiguous pronoun it. Like if you only look at it, you don't know if it's talking about the animal or the street. But by looking at self-attention, the model is able to relate that animal refers to it because an animal can be described as tired, whereas in this sentence, a street is more often described as wide, so street refers to it. And so like this is like crucial, for example, if you want to translate this to a gendered language like French, where the pronoun it will have different forms like elle or il, depending on whether it's an animal or a street. And so this is a more formal description of the self-attention mechanism, if you're interested. So like, for example, if you want to like calculate or translate the word thinking, and you want to obtain the context-aware like representation of thinking. So you do that by first, so this is the embedding of the word as a vector, and you get the query and the key and the value of the current word. And this is a linear transformation of the embedding, and where the weights are trained during while you're training your model. And then you can obtain the score by getting the dot product between the query and the key of another word. So this score represents like how important the key is in order to resolve the query. So for example, like the score 96 shows like how much attention we need to give to the word machines in order to understand the word thinking. And then like you divide by 8 and you do the softmax, and this is just for like gradient stability and for normalization. And then in the end, you get the final representation of the word with self-attention by getting the weighted sum of each score multiplied by the value. So this is a representation where like you enhance words that are important in order to understand the word you're translating, while you make like the other words that are irrelevant die out in the final sum. Does that make sense?
Yes.
Okay, cool.
Mm.
Yeah, so like this is what the encoder looks like in more detail, where each layer is composed of 2 sub-layers. So we have the multi-head attention mechanism that I just explained. And then we also have a feed-forward layer. And so decoder is very similar, but it has like an additional attention layer, which calculates the self-attention between the decoded word and also the previous like encoder representations. And at each time step, the decoder produces one output, and then it's fed back into the decoder while using also representations from the encoder in order to get the next word translation until it reaches the end of sentence token. Okay, so now I'll move on to the experiments I performed. So to evaluate and compare the performance of my model to existing works, I used the RWTH-PHOENIX-WEATHER 2014 T dataset. And this data.
How did you zero in on the data set, Kayo? Was there anything, because there are lots of data sets? Yeah, how did you zero?
Yeah, so the thing is, there's not that many data sets in sign language. And as far as like I know, but when I was doing this research, this data set is the only like challenging benchmark for sign language translation, where you have both the video and the gloss annotations and the German translations in a parallel way.
Okay.
Yeah.
Got it.
And this is also the benchmark data set that is the most commonly used for the sign language translation task.
Understood. Thank you.
Yeah. So this dataset consists of a parallel corpus of German Sign Language videos that comes from weather forecasts, where we have 9 different signers in the videos. And the gloss annotations have a vocabulary of 1,066 different glosses translated into German. And so the previous dataset only has 7,000 training pairs, whereas as most of you know, like deep learning models, notably transformers, they achieve better results on larger datasets, which is why I was also interested in assessing the performance of my model on a larger dataset, and also in a language most of us are familiar with, like English. So for this purpose, I also conducted experiments on the ASLG PC12 corpus, which is a corpus that is produced in a semi-automatic way, where they use rule-based methods in order to extract glosses from English phrases. So this corpus does not have the videos, and it only has the glosses and the English text. But as you can see in the table below, this corpus is much larger in size, with a vocabulary of like 15,000 ASL glosses and 21,000 different words. Yeah. And also many of the ASL glosses, they're actually just English words with an added prefix. So during data pre-processing, I removed all such prefixes since they did not provide much information. And since the vocabulary was so big, I also set all words that are rare in the corpus, so that appear less than 5 times during the training dataset as the unknown token, which allows us to reduce the vocabulary size considerably and reduce the complexity of the model.
So when you say you remove the prefixes, like, can you give an example? Like, what did you actually remove? Like in an example?
So for example, like there are glosses that said, I don't know if I can show an example right now. Like, let's say like there's like tomorrow as a gloss, but then there's a prefix that CL hyphen tomorrow. because like CL means that like there's like a clause attached to the sign. But then like for me, when I looked at it, like tomorrow gives like all the information you need in order to do the translation. So like I reduced that to make it more similar to English.
Got it. Thank you.
Yeah, thanks for, yeah, like feel free to like ask some clarifying questions.
Yeah, please continue.
Yeah. So yeah, so like this is the setting of the first experiments that we did, where we performed translation on the ground truth glosses taken from the dataset itself. So this is an experiment that tries to assess the performance of our translation model when it's used with a perfect CSLR system, which is like a sign language recognition system that produces gloss annotations with 100% accuracy. And gloss to text is a text-to-text translation task that is both novel and challenging compared to classic translation tasks between spoken languages because of the high linguistic variance between the source and the target sentences, and also the scarcity of data we have, and especially because of the information loss or the imprecision in the source sentence itself, because gloss is just like another representation of the original phrase. And so in my experiments, all my transformer models are built using PyTorch with the OpenNMT library. I'll provide a link to my GitHub repo at the end of the presentation. And during training, the networks are evaluated on the development stat at each half epoch. So early stopping is applied with patience 5 in order to stop the training. And we use beam search for the decoding, and also where in decoding, a generated unknown token is replaced by the source token having the highest attention weights. So this is especially useful when the unknown symbols correspond to proper nouns that can be like directly transposed between languages. And since our architecture varies highly from previous works in sign language translation, and especially since transformers are very sensitive to hyperparameter and architecture settings, which make them very hard to train, I performed a series of experiments to find the optimal setup. So I will present like some of the interesting like findings during my parameter search at today's talk. But for the full detail, you can also look at my paper. And I also like made many experiments with various techniques that are often used in classical NMT to sign language, like transfer learning, weight tying, and model sampling to improve model performance. So the first like experiment I did was on the model size. So the original setup of the transformer architecture, and like in most transformers for spoken language, people use 6 identical layers in the encoder and the decoder. But our task is very different from a standard machine translation task between 2 spoken languages. So I tried like training networks with 1, 2, 4, and 6 layers. And I find that using 2 layers provides the best results. And so to choose the best model, I mainly took into account the blue 4 score, which is the metric that is the most widely used for machine translation. And this is the metric that only compares like the subwords between the source and between the translation and the reference itself, and like sees like how many like subwords are matching in the 2. And yes, like evaluation is another ongoing challenge in machine translation in general, because it's hard to assess when a translation is good, and sometimes like 2 sentences that doesn't have like the same word like syntax or the same words at all can also like give the same meaning and can be equally good. Yeah, that's another challenge for another day. Yeah, so for both the RWTH-WEATHER dataset and for ASL, I find that using 2 layers gives the best results. So like this is probably due to because our dataset is much smaller than those used in standard machine translation tasks. So larger networks are more disadvantaged. And also the ASLG dataset is a larger dataset, but the task at hand may be more simpler, which also explains why smaller networks are more suitable. And I also tried experiments with many different embedding schemes. So embeddings are really the key to how the model understands words. And like, so here you can see how a good embedding gives like similar vectors in the projection for words that are highly related. So this really helps the model like knowing, or at least like to process each word in a sentence. So optimizing how the words are embedded can really enhance model performance. So one like first thing that I tried is called weight tying, where we share the embeddings between the input and the output in the decoder. And this is like a really good method for regularization. And another thing that I tried was, it's called transfer learning, where pre-trained embeddings are widely used in NLP, where we initialize our models using pre-trained word embeddings that were typically trained in an unsupervised manner on a large corpus of text in the desired language, so very often on Wikipedia articles. And this can help bring in outside information at the start of training. And it's especially useful when you're dealing with a small data set, so like because you cannot learn enough information from only the data you have. And since German is a high resource language where many German data resources exist, so several pre-trained German embeddings are available publicly. So I I used the GLOVE and the fast text pre-trained embeddings. And to the best of my knowledge, pre-trained embeddings have never been used on sign language translation in previous works. And there's only one matching token, as you can see here, between the German glosses and the vocabulary in our embeddings. So for this reason, in my experiments, I only initialized the pre-trained embeddings on the decoder side in the German language.
So, Kayo, in transfer learning, do you have to do any fine tuning as well, apart from using the pre-trained model? Do you do any fine tuning?
Yeah, exactly. So so here the pre-trained embeddings are only used to initialize the model, and then so like we do not freeze the embedding layers after when we're doing the fine tuning on the data set, and so these embeddings are fine tuned and like changed again during the training. But like it's like it gives like a kick start to the model, or like it provides like some help to the model to get the training going.
Okay. Thank you.
Yeah. And yeah, so in my results, so on the German data set, transfer learning or weight tying actually did not improve performance. So one possible reason is that the data is too small for the model to learn the difference in domain between the weather forecast and the data set, the Wikipedia data that was used for the pre-training. And also weight tying can reduce the model complexity too much, which is why I kept random initialization and of word embeddings from my other experiments. But on the ASL, when I used the pre-trained embeddings, yeah.
Sorry to interrupt. The thing is, why didn't you go for transformer-based embeddings as well, like BERT or something?
Oh yeah, so that's a good question. And yes, like I could have, but yeah.
Are
Yeah,
you
that's a good
planning
question.
to try out results with the BERT or transfer-based embedding and continue the research or something? No.
Yeah, so I guess in my initial experiments, I just want to see if transfer learning is a viable approach for sign language, which is why I train with the most like readily available and the most popular pre-trained vectors. But like since here, so for ASL, the fast text embeddings actually improve performance. So I think that like when we have a data set that is large enough, it is definitely interesting to try to do transfer learning from spoken language to sign language, and it is worth doing experiments on like BERT-based embeddings, for example. Yeah.
One more question. Since you tried using transfer learning with the with sign language recognition, which was pretty much new, like what do you suggest of using maybe an ensemble learning model to capture more features? Like
yeah. Well, the funny thing is my next slide is precisely on ensemble learning, so
okay.
I'll get back to that in 1 minute. Okay. Sorry, let me just drink some water.
Thank you. Yeah.
Yeah, I had one more question, Kayo. Like you mentioned that the disadvantage of using this transformer was that it is hard to train. So what do you mean by that? Can you give
So yeah, so it's hard to train because if you don't have the right hyperparameters, you can obtain very bad results. Like this does not mean that the model is not well adjusted to this task. So for example, like before I did this research, there were already like at least 2 papers I knew of in the computer vision community that did use transformers for sign language translation, but their results did not surpass the previous recurrent network models. And I suspect that this is due to like, because the hyperparameter tuning was not done enough, and which is why like their models were not able to outperform the recurrent networks. Yeah.
Okay. Thank you very much.
And like this is why it's very important to like do all these experiments, especially for a very new setting like sign language, because like the task is very different from what the like most literature in transformer does. So you cannot like just use the exact same features for spoken language translation as in sign.
Got it. Yeah, thank you.
Yeah. Yeah, so I guess I'll talk about ensemble learning now. So like these are methods that combine the prediction of multiple models, and they have shown to improve the overall performance in a wide range of tasks. So I propose to use ensemble decoding, where a group of models that have been trained separately can be used together during the decoding phase by combining the output of each different model by averaging their prediction distributions. And we use the average in order to give our final prediction. And so like ensemble learning, in a nutshell, it's nice because it can help amplify models, like specific models where the model is performing well. And then like, so let's say like model 1 is like good at translating sentence A, and model 2 is also good at translating sentence A, but model 3 is bad at that. So like model 3 is not taken into account that much, but then maybe model 3 and model 2 are like really good at predicting the next sentence, while model 1 is bad at doing that. So like it kind of helps get the best out of each model. And yeah. So like I used I chose the 9 models from my experiments that gave the highest blue score during testing for the German Sign Language. And the number of models is chosen empirically because if we use 2 little models.
Sorry, Gayo.
Yeah.
Just one curiosity. When we are performing ensemble learning with this, is it necessary that the input has to be common? Can we not use input from same, like for one thing you're using just segmented hand shapes, and for second thing you're using the tracking of your hand or something? Can we use different input in ensemble?
Yeah, so I think that ensemble learning in general, it's when you use the same feature, the same input in order to like compare or like combine the models on a common input. But like, you can also do like separate features from separate models. Like that would more be like I would think more like a single model where like each model processes the individual cues, and in order to like combine the different information that all the different model gives, and in order to like combine one unified output, if that makes sense.
Right. Like putting all the outputs into probably an LSTM or something.
Yeah. So it's like different models that provides different features, and then like one meta model that combines all of them. But like I wouldn't call that ensemble model, but like I'm not sure if people would call it ensemble. Yeah.
Right. Like not a feed forward network, but a feed forward model network, something like more complicated. Like,
Yeah.
And Kayo, is there a disadvantage because you're running the same, you're giving the input to multiple models, and each model is trying to process the same input? Is there any advantage to ensemble decoding?
Yeah, so I can show you in the next slide how like ensemble decoding like gives like a better results without doing additional retraining to our models. Because like I said, like this helps like taking parts like amplifying models when they are like performing well, while like attuning them or like drowning them out when not doing very well. And it helps like try to like take the best of the different models.
Got it.
Yeah. And so like so these are my final results. And I also experiment with like learning rate, batch size, and beam size. But for the brevity of this talk, I can go to my paper if you're interested in that.
Yeah.
Yeah. And so this is the final results I obtained on the German data set. And you can see here that, so this is our single best transformer. Well, this is the ensemble of transformers. And without any additional training, just ensembling alone improves the blue 4 score by over 1 point on testing. And we also reported an improvement of over 5 blue points on the current state of the art, which is in the second row. And the third row is a contemporaneous paper. Like the paper appeared like at the same time as I was doing my research. And they also have similar results with the transformer that outperforms recurrent networks. So like this really shows the advantage of transformers over previous sequence-to-sequence networks for sign language translation. And I obtained similar results for the ASL GPC12 dataset. And the only difference is that I don't get as much improvement by doing the ensemble. So like one reason for that can be that the performance is already very good. So in order to like have additional changes, like without making substantial changes to the architecture, it's hard to get more increase on that. And another explanation might be that the different models in the ensemble are like they're very similar to each other. So when the models are very similar, ensembling has little effect because like there's not going to be much differences between taking all of them together or taking just one of them. So now I'll move on to the second part of this talk, which is on video to text translation. And this is the work that is presented in my paper that is going to appear very soon at the International Conference on Computational Linguistics this year.
Very good. Congratulations. So this
Thank
is
you.
already done? You already presented it? Or when is it? Conference?
So the conference is in mid-December, I think.
Okay.
Yeah, and it's going to be online.
Yeah, it's supposed to be where? It was supposed to be.
It was supposed to be Barcelona.
Okay.
Yeah.
Okay. Yeah, please
and like
go ahead.
I'm currently working on the camera video for this paper.
Okay. Very good. Yeah.
Yeah, so in this work, I performed video to text translation where I no longer use the ground truth glosses for the translation. And so to obtain the glosses from the video, I use the spatial temporal multi-cue network. And my work is the first to use this architecture for sign language translation. So in this model, we have a spatial multi-cue module that has a self-contained pose estimation branch, which decomposes the input video into different spatial features of multiple visual cues. So there's a different cues for the face shape, the hand shape, and the full body, and also the pose of the signer. And then we have a temporal multi-cue module, which has stacked TMC blocks and temporal pooling. And this calculates the temporal correlations either within the different cues or between the different cues at different time steps. So this helps to preserve each unique cue while also exploring the relations between the different cues at the same time. And this is important because in sign language, like the cues, like they have to be processed at the same time because they really relate to each other and they construct with each other in order to convey the information. And finally, the inter-cue information and the intra-cue features, they're analyzed by bi-LSTMs and connectionist temporal classification modules for sequence learning and then inference. So this architecture efficiently processes multiple visual cues from sign language video in collaboration with each other, which makes it very effective. And it achieves the state-of-the-art performance on 3 sign language recognition benchmarks. And including the PHOENIX-WEATHER 2014 T dataset that we're working on, where it achieves a word error rate of 21 for recognition. So my very first experiment is a very simple one, where I just used the best performing model from the previous experiments on gloss to text translation. And I simply feed that the output of the STMC network to obtain the German translations. So without doing any additional training and just using the model itself. And despite having no additional training, this model, which is here, it obtains a relatively high score. And the performance is only like slightly inferior to the prediction of the ground truth glosses that we had before. Oh, I forgot to include that in the table. I should have included before. Yeah, but if you remember, we had 24.9 for the ground truth. And here we have 23.77. Yeah. So, so like there must be like slight variance between the ground truth glosses and the STMC network outputs, which is why this model that was trained with the ground truth glosses is better suited for that. But the glosses still have enough similarity for the model to provide good results, despite never having seen the STMC glosses during training. And so in the second part of my experiments, since there is no existing work that performs translation with the STMC network, I also trained the sequence-to-sequence networks with the recurrent gates, taking the same architecture as the previous works, using either Badanal or long attention in my STMC-Transformer framework, or should I say STMC-RNN. So the recurrent sequence-to-sequence model obtains slightly better performance with a long attention. But like what is surprising is that for recurrent sequence-to-sequence models of similar architecture between the ones that I trained here and the ones in the previous experiments here, where they also use the RNN, our model that translates the output of the STMC model provides better results than the baseline model that translates the ground truth glosses.
And Kai, out of curiosity, which lab is the other models from? Because it seems from the same author, all the four
yeah,
models.
These are all from the RWTH University at Aachen in Germany. And so Kamgons, he's the author that introduced sign language translation for the very first time. And he does lots of like very interesting work on sign language processing.
Is that the neural sign language translation paper?
Exactly, yeah, from 2018. So the results here in 2018.
And I guess he's the same person who was anchoring the sign language recognition workshop at ECCD.
Yes, yes.
I remember his GitHub name, Nikam, N-E-C-A-M.
Yeah, exactly. Yeah.
I've used and.
Yeah, like he's a very he's a great researcher and he's very nice. Yeah.
Right. I emailed him for a computer vision talk as well. He said that mail me in fall, I'll be available.
Yeah, he's probably very busy. Yeah.
But he was kind enough to answer. So,
yeah. Yeah, he was actually the one. Like after I published my paper on arXiv, like he was the one who contacted me to submit my work to his workshop. So I'm grateful for that. Where I was like, I don't know if I would have found the workshop. Yeah, that was very nice.
Like since you just mentioned it, I also have this undergrad doubt. Is it a good idea to write a paper and put it on arXiv and share links on Twitter and everything and let people reach out to you for relevant conferences?
Yeah, so from my experience, at least, I think it was a good idea because like instead of waiting for peer reviews, it allowed me to bring my work out early on. And like this really helped like more people who like become interested in my work. And I also like met like other researchers who work on similar things because of that. So I do encourage that, yeah.
So if I am writing a paper someday, I can put it on arXiv and then send it to conference for reviews and everything.
Yeah. And the only thing you have to be careful about is for anonymity period, because like many conferences, they have a period where like 2 months before the submission deadline, you are not allowed to talk about your research online. So this means that you're not allowed to so if you already put it on arXiv, then it's fine before 2 months, but you cannot publish your paper on arXiv during the 2 months period.
Okay.
And you cannot also like talk about your research on Twitter or anywhere public.
Okay. So you have to remove it from arXiv.
You don't have to remove it.
No, it's just done to make sure that the reviewers are not influenced by the.
So this is to preserve the double-blind reviews so that reviewers don't know the author when they're looking at the paper.
See, basically, when you have the double-blind process where the reviewers do not know who the author is, if it's already in public domain, the reviewers might be influenced by public perception. That is the
yeah.
Thank you.
Good.
Yeah. Okay. So this is my last slide of results. where I finally trained transformer models with the same architecture in the last experiments. But I ran a hyperparameter search again for the learning rate and the beam size, and I used the 8 best models in an ensemble. And so the end-to-end, the video-to-text system of the STMC network with an ensemble of transformers gives an improvement of over 7 blue points on the current state-of-the-art for video-to-text translation, which is compared here. And a single transformer also improves the performance by over 2 points compared to using the recurrent models. So this again confirms that transformers are well suited to the task of sign language translation in different settings. And so one result that I really want to talk about is that again we observe that transformers obtain better SLT performance by translating the STMC network. Because when I did the gloss to text translation before using the same architecture, I had I had a blue score of 24.9, whereas here I have 25.4. And this is very counterintuitive if you think about it, because in the first setting, you're using the ground truth glosses. So this means that you're simulating a perfect sign language recognition system. Whereas in this setting, the STMC network, it's not a perfect sign language system. It does not have an accuracy of 100%. And this result is repeated to the transformer and the recurrent model. So, while the STMC network performs imperfect recognition, it seems that the predictions of glosses it gives are better suited for sign language translation than the actual ground truth annotations. And they are more readily analyzed by the translation model. And so all of this is very surprising. It's not impossible because the glosses, they're only a simplified intermediate representation of the original sign language. So it's expected that even the ground truth glosses can contain imprecision that can negatively affect SLT performance. And this result is also a counterexample to the claim in the neural sign language translation paper, where they stated that the gloss to text performance acts as an upper bound for the translation. Whereas here, we have an example where sign video to text translation outperformed gloss to text translation. So to conclude, so there's 2 main takeaways from my research. And so the first takeaway is that although there have been many previous works in the CV community that also applied transformers to SLT, they couldn't beat the recurrent models, likely because of the hyperparameter settings we talk about. But our experiments demonstrate that with careful tuning on a new translation task, transformers can obtain better SLT performance than with the previous RNN-based networks. And we also showed that NLP techniques like transfer learning can also apply to sign language. So this really shows that sign language processing is both a visual processing and a linguistic problem. And this line of research will really benefit from the computer vision community and the NLP communities working together. And
I guess, is there some network issue from?
Yeah.
Okay,
Kayo, can you hear?
Okay. Yeah, so hi, I'm back. So I was saying, so a key finding is that we get better performance by using a SMC network, which really calls into question the current methods we're using because the glosses themselves are suboptimal. So if you think about it, in the current design, we're training to make the tokenization model output glosses that does not give the full information we need for the task. So, and that underperforms some other glosses that we might have. So this means that no matter how good our recognition model becomes, it will actually not benefit translation performance and can actually give worse downstream translation performance. So I think this is a very important issue. And it really tells us that we have to reconsider how we're performing the translation. So for this, I have 2 suggestions. So the first suggestion for future translation is that is end-to-end training without gloss supervision, which is a one promising step. And so a recent paper did perform this where they used transformers for the recognition and the translation. But like their end-to-end model did not yet surpass their other model that performs joint training. So as future work, I suggest continuing work on end-to-end training for the recognition and translation models so that the two optimize at the same time. And the recognition model learns an intermediate representation that can optimize translation. And the second suggestion I have is to think about like using other forms of intermediate representation other than glosses. So like one idea would be to have a representation that encodes the information in a more fine-grained way, such as employing multiple channels for each cue, like having one channel for each hand and like one channel for the mouthings. So like there's also some work that started to look at like other annotation configurations for sign language translation. So yeah, so like that is all I had to say for this talk. So thank you so much for joining me and for participating. And please let me know like if I'm open to questions and yeah.
Yeah. Thank you very much, Kayo. I just had one clarification in the slide in where you showed ensemble modeling. I think you showed an averaging of the output, but it is actually you're just taking best of one of the models, right? But where you had model 1, 2, 3, and it went to an averaging thing. But I don't think there is any averaging done. You just take the best of either.
Not exactly. So the average thing is that so like each model gives a probability distribution for the sentence. Like for example, like in the target sentence, like it assigns a probability for each word position, like what the highest probable word is for the translation. So what we do is that we take the average of all of these probability distributions. So let's say like for the first word, like the first two models assign probability like 100 to the word the, and then the third model assigns probability like 80% to the word it. Then like the final word that is going to be taken is the, because like the average the has like the highest probability. So yes, like that's what the ensemble model does, if that makes sense.
Okay, got some vague clarity of, because I thought it was just the best of them. And
Thank you so much. Like the primer was very helpful initially. I believe everyone who will be viewing the talk, the initial introduction about transfer learning and transformer stuff will be very helpful.
Oh, okay, cool. I'm glad to hear that. Yeah.
Kaya, I had one general question. Have you ever seen somebody using transformers for transfer learning in time series data? Have you seen it?
For time series data, oh, so I have to admit, like I don't have much experience in time series analysis, so I'm not aware, but I wouldn't be surprised. Yeah, but like then, like you should like ask yourself, like what kind of data would you want to transfer for time series data? Like what kind of pre-training would you want? Yeah.
Yeah, so because let's say you have let's say two data sets A and B, and you have, but they are similar, let's say for a similar product or whatever, but you have more of data set A and less of data set B. So you just want to train it on A and test it with B, something like that. For similar products, let's say you have stock prices of similar products, but for product B, which does similar function, but you don't have as much data as you have for product A. So in those cases.
So I guess like it can be possible, like as long as like you pay attention that the two like different domains are similar enough in order to like actually have like common data that can be transferred from one to another. Yeah.
Good. Yes. Anything else, Shambhavi?
No, sir. I'm pretty much
Good. Yeah, I think we can stop recording.